Okay, this is Statistics from McGarrett, Lesson 3 continued. We had a bit of a technical difficulties. So we're going to start off about where I left off. So what I was saying was, so you have a scatter plot, and what you need to do when you look at the scatter plot is first you need to decide if you have a relationship that's linear or curved. Right? This is clearly a very strong relationship. These variables are clearly associated, just like these are. It's a positive relationship. But this one is linear, right? This is a straight line. This one is curved. For correlation, you cannot use correlation to look at a curved relationship. You can only look at a linear relationship with a correlation. So if you have a curved relationship, you have to either transform it or do something to it to make it not curved and to make it linear. And we're going to talk about that in the next lesson. But if you have it linear, then you can use a correlation. Okay, the other thing that you need to think about before we actually go into correlation is you need to think about underlying variables that are not graphed. So maybe you measured these plants 2 times a year. So maybe you measured plants in June and in August. And maybe what you find is that plants are here in June, they're measured in June, are all here, and then plants that you measure in August are all here. Right? There's nothing in this graph that shows up that you only measured plants or that you measure plants at 2 times a year, yet that clearly would have a relationship and might affect what kind of things you see here. So you need to be careful about underlying variables that aren't graphed, but that could actually have a strong effect on the graph. And so whenever you're looking at your data, you need to think about that. Okay, so now that we have that, we're going to go into correlation. So there is, so first of all, we're going to erase this. This is a curved relationship, so we can't deal with it, with the correlation. So instead, we're going to look at only this relationship, this linear relationship. So what a correlation measures, so first of all, if you just look at the word correlation, what is it? It's a correlation. It's a relation between 2 variables. It's a correlation. And what correlation does is it measures, it's just really a number that measures the strength and direction of a linear relationship between 2 quantitative variables. Right, so the keywords here are, first of all, strength and direction rather, and then linear and quantitative, right? So we're looking at quantitative variables, and it has to be a linear relationship. So it has to be linear, and you have to have quantitative. If you have categorical, you cannot use it, and if it's not linear, you can't use it. And then, but if you have these 2 things, right, linear and quantitative, then what correlation does is it measures the strength and the direction of this. So what does that mean? Essentially, what correlation is there's a correlation coefficient which is called coefficient. It's called R, letter R. And R is really just a number. Now, if you're interested in how you derive this number, it's on page 127 of the statistics textbook that Selenga has copies of. But really, what you're going to be using to calculate R is you're using a statistical package. You're using software, using Excel or R or some other stats language. By the way, you might notice why the stats program R is called R. It's because of this letter, because of the correlation coefficient. Okay, so what R really measures is the strength and direction of a relationship between 2 quantitative variables. R goes from -1 to 1. So it can be any value like 0.8 or -0.99 or 0 between -1 and 1. And what this means is if you have a relationship of -1, that's or 1, you say that two variables are perfectly correlated, which is to say that they fit a perfect line to each other. So they would look like this. So this is a positive relationship where it's going up as one variable increases, the other increases. A negative relationship, we'll do that in a different color. A negative relationship would be if they're going like this. So they're perfectly correlated. So this is 1, and then red is -1. What happens if you have 0 is that you essentially have a cloud of points. Is that if you know something about one variable, that tells you nothing at all about the other. So if you know anything about x, you know something about x, that doesn't tell you anything about what y is. There's no relationship at all. So this is 0. This is when r is equal to 0, is that you got nothing. There's no relationship at all. And then something like this, right, is a very strong relationship. I would guess that this has, and it's positive, and so I would guess that this has a correlation coefficient of something like 0.97. That's it. Those two variables are very closely related, our graph there. Now there's something else to think about, which is if you have these relationships, I said this is 1. Here's also r of 1. This is also 1. Let me draw this in different colors. It doesn't matter what the slope is. You can have any slope at all that's positive. If it's 1, right, they're just on a line. You're not measuring the slope. You're just measuring whether they're closely correlated and whether they're positive. Right? All of these lines, right, this line, this line, this line, this line, they all have an r of 1. Doesn't matter that they're different slopes. They're still r1. They're still an r of 1. And same thing for negative. It can be any slope. I can be point this way, point that way, point that way. There's still r of -1. Okay. But 0 always looks like this. Or close to 0 always looks like this. Okay. So, let's see what the next step here is. Right. So what we're going to do is that there are several things you need to know about correlations that I need to refer to my notes here to remember to put all of them. So one is that there's no distinction between explanatory and response variables. Variables. So what that means is that height here and number of seeds has an R of 0.97 regardless of if you look at height to seeds or if you had seeds here and height here. So you can flip the x and y axis and the relationship, the correlation remains the same. That'll always be 0.97. That's different from regression, as we'll see. So that's important. So what that means is that you don't need to have a causal relationship or think that one variable influences the other to get a correlation. Is that you can flip those and it doesn't matter. But that with regression, that's different. So the second is that there are no units. This is a unitless number. What that means is that if you measured height in centimeters and you decide that actually you want to measure them in millimeters, and so first you calculated your correlation with height in centimeters, you now want to change it to millimeters, it doesn't change it. You don't need to redo this. This correlation remains the same regardless of what units you put here and what units you put here. The correlation will remain the same. Now, if you change these units, these points might, instead of going like this in this angle, they might look at this angle, right? But as I said, point 1, right, it doesn't matter what the slope is. it'll have the same correlation coefficient. So that means that units don't matter for either the x-axis or the y-axis. It's a unitless number. And that's different from regression as well. So the other thing, as I alluded to earlier, as I said earlier, is that it's susceptible to outliers. So you need to be careful if you have outliers. So what that means is that that's very similar to a mean. So if you think about, if we had 10 people in this GARE, then we took the average weight of everybody, and let's say that 9 people weigh about 75 kilos, and then one person weighed 180 kilos. He was very fat, right? That very fat person would skew the average. It would pull the average way up, as opposed to if that person just wasn't in the GARE, right? When the average would be 75 and be very close. Without one person, the average might be 85, because the mean is susceptible to outliers. And correlation is exactly the same way. So if you have numbers that look like this, so if you graph whatever you have and it looks like this, you have points here, let's say, and they have a point here, this will look like a very strong relationship because of just this value, just that one. If you erase that value, this is nothing, right? This doesn't look correlated at all anymore. But if you add just one point down here, you can say, "Ooh, hey, look at that. There's a strong correlation," right? So that means that correlation is susceptible to outliers like this. So you need to be careful if you have data that look like this. We have 1 or maybe 2 points out here, then you need to be careful about how you deal with it. Okay, so I'm going to erase that.